For today's homework help, we're going over problem 5 on page 2. And problem 5 says, on a cold, wintry day, the temperature outside hovered at 0 degrees Celsius. Karen made herself a cup of cocoa and took it outside, where she would be chopping some wood. However, she decided to conduct a mini science experiment instead of drinking her cocoa. So she placed a thermometer in the cocoa and left it sitting next to her as she worked. She wrote down the time and the reading on the thermometer as shown in the table below. Right, so in this table we have the time since the first reading. Right, so we have I presume these are minutes, like 5 minutes, 10 minutes, 12 minutes, 15 minutes. And then we have the temperature in degrees Celsius, right? So it starts out pretty warm at 24.41 degrees Celsius. Right after 10 minutes, it's less than half of that heatness or temperature, right? So now it jumped from 24.41 to 8.51. And in 2 minutes, it drops down like about another 3 degrees, goes to 5.58. Right? And then in 3 minutes, it jumps down like about 3 degrees as well. So we see that this, right, we've been working on a lot of problems. When we have exponential functions, we were working with a lot of problems that were exponential growth, right? They were getting bigger. But we see here that it's getting smaller. So the opposite of exponential growth, right, is going to be exponential decay, right? So for growth, we see that the graph gets bigger and bigger and bigger. We have exponential decay, where it jumps down really quickly, then kind of flattens out near the bottom, and it never actually hits 0, right? So we've used like exponential growth for problems that involve like virus spreading or the population of either humans or rabbits growing. So exponential decay is used for stuff that is decaying, right? So like it's used to model like radioactive substances because they're slowly decaying away. Or sometimes they're used to measure like the amount of a drug in your body, right? Because the amount of drugs in your body have a half-life. So after like a certain amount of time, it'll reduce by half. Then at another certain amount of time, it'll reduce by half of that. And another amount of time, it'll reduce by half of that. And each time you're going down by half. But you'll never actually make it to 0, right? So that's the interesting thing about exponential decay. So back to our original problem, right? So same thing as before. We are going to plug them both into an equation that looks like y equals a times b to the x, right? So what we're going to do is we're going to pick 2 points, right, from this table to plug into here. So just as a quick note, it's there should be something to tell you that it's right, decaying, or that we're using an exponential function here, right? Or right, you got to get used to knowing your scenarios. Like you got to think about it. Does it seem like when you have like a hot coffee or hot cocoa, does it seem like it cools down at a constant rate? Or does it kind of flatten out at a certain point, right? And obviously it flattens out at a certain point because if it grew at a constant rate, that means it would keep on getting colder as time went on. Which means like eventually it'll be like super ice cold frozen, which of course we know it never happens. Right, so this is an exponential decay function. And then we're going to plug it in here. And then the points that I'm going to pick right? So a good idea here is to always pick the points that are closest together, right? So we could pick so I'm going to pick the 10 and 12 points, right? 10, 8.51 degrees, 12, 5.58 degrees, right? Those are the closest 2 points together in terms of their x values, right? 10 and 12, right? They're only 2 away. So remember that the x value is usually time, right? So since the x value is time, right, we're going to plug these in for x, 10 and 12. We're going to plug these in for y, 8.51 and 5.58. Right? 8.51 degrees after 10 minutes, 5.58 degrees, right, after 12 minutes. So now, right, we're going to do the same thing that we were doing yesterday. So what we do is we want to solve both equations for A. Remember, and the reason why we're doing this for A and not B is because B and the B's have these exponents attached to them. This A is just straight up and normal, so we're going to solve for A. Right, so that way we could eventually use the equal values method of solving a system of equations. Right, so all we have to do here is divide by b to the 10, right? And we just get the b to the 10s cancel out. And we're just left with 8.51 over b to the 10. Give you a couple seconds to write that down. And then we're going to do the same thing here, except instead of dividing by b to the 10, we're dividing by b to the 12. The reason we want to divide by b to the 12 is so that way the b's cancel out. And we're just left with a equals 5.58 over b to the 12. Alright, so we're making some good progress here. So the next thing we got to do, I'll give you a second to finish writing this down just in case you need it. But remember, we could use the equal values method now because both of the equations are in the form A equals, right? We know that A equals 8.51 over b to the 10. And we also know that A equals 5.58 over b to the 12. Therefore, we could conclude that they equal each other, right? Since they both equal A, both this guy equals A, this guy equals A, so we know that, right, by a transitive property, right, we know that 8.51 over b to the 10 equals 5.58 over b to the 12. So now what we're going to do is we're going to do our proportion equation, right, where we multiply both sides by b to the 10 and b to the 12, but in practice it kind of looks like we're just multiplying across. So right, so the b to the 12 will stick to the 8.51, and then the b to the 10 will stick to the 5.58. Right, because we were multiplying across to simplify that proportion. So now that's good. So, right? So now we're going to take the smaller exponent, right? The exponent's 12, b to the 12 or b to the 10. Which one is smaller? Well, b to the 10 is smaller. So we're going to divide by that. Right? Both sides we're dividing by b to the 10. So we just rewrote this line, and then we are dividing by b to the 10. Right, so that way these guys cancel out. And then for the left side, right, if you have 12 b's in the numerator and 10 b's in the denominator, right, when you cancel them out, right, you're only going to have 2 b's left over, right, because, right, also remember that it is, right? When they cancel, like in a fraction, it'll be subtract. So you subtract the exponent of the numerator minus the exponent of the denominator, right? 12 minus 10, which gives you 2. So now, right, the 8.51b squared equals 5.58. And now we just got to divide by 8.51 on both sides. So that way these guys cancel out. Okay, so, and then we got to use a calculator. So let's pull up Desmos.com. And we're just going to say 5.58, and then remember divided by 8.51. It's like 6.6.5, and we could round that up, right? So 0.6.56. And then, right, so now we got to think about, like, what can we multiply 2 by to get to 1, right? Or we'll do this intermediary step where we raise both sides to the 1/2. But you could also remember that whenever you have b squared equals like a number, right? The way how you find b is just by taking the square root of it. So I did this method here just because this is what we were doing last class. And when you're doing problem 4 today, right, you could model it the same way here, right? Remember, we're trying to get rid, we want b to be alone. So we're trying to get rid of the 2. So the way how we get rid of the 2 is by multiplying by the reciprocal of 2, right? The reciprocal of any whole number is 1 over that number. So that's what we do here, right? And then since we raise this side to the 1/2, we have to raise this side to the 1/2. And remember that you always drop down this denominator outside of the root. So, right, even though you don't even need the 2 here, because if there's no number, it's assumed to be a 2, I put it in there just so that way you could use this to model off of number 4. So then we just got to find the square root of 5.56, and it's, right, we could like pull out our calculator again. Right, so even if you right, we could still do it this way, right? We go to miscellaneous, and we do the nth root, we'll put 2 there. Even though it's redundant, we don't need it, but I'm just showing you so that way you could use it for other problems. So the square root of 6.56 is 2.51. What? .51? 0.81? How does it get that? So we got 0.81. And so now we're just going to plug 0.81 back into the equation here, right? So we have 8.51 over that to the 12th. So we type it into our Desmos calculator. So we'll say 8.51 divided by, say, 0.81. Then we want to raise it to the 10th. And we have just about 70. Oops. So that should say 70. All right, and then we just plug it back in to our equation for a times b to the x. And we get y equals 70 times 0.81 to the x. and I'm going to get back to you guys.